So how to solve a differential equation using power series. Okay, I think all the screen is uh, being being displayed. Good. Um, Section 6.1, half of it is a review of power series from chapter 9 in the Larson calculus textbook. Chapter 9, section 6, 7, uh, uh, I think sections 9.6 to 9.10 is where we dealt with power series, how to solve using McLaren and also the Taylor expansion. Two things that you need to remember here is how to write a geometric series and then how to apply the so-called ratio test to determine convergence. We'll make use of those two ideas. Here, the test would be on whether or not a particular power series is convergent. And here we examine convergency in terms of about a point or in the neighborhood about that particular point on some interval. So we're taught in terms of convergence in three ways: that a power series that is a differential equation, which is being represented by a power series, may be convergent, that is, it has a solution at one point. It may be convergent, or it has solutions on an interval, or it may be convergent everywhere on the number line. Well, that also will argue the question that if it's convergent only at one point, that means it's divergent everywhere else. Right? That just goes to reason. If it's convergent on an interval, then beyond that interval it's divergent. Right? If it's convergent everywhere, then it's never divergent anywhere. Okay? So, um, so two things here. Let's see if I can pull this screen over. Where is that? They don't have anything in the bottom that I can pull this over. It doesn't do it. So two things to recall: geometric series and the ratio test. I think you can see that up there on the screen. The objective I've already stated. So here, recall the geometric series, and I know it's in blue. Bless you. Yes, sir. It may be difficult to see, and I do apologize for that. But this is just the so-called geometric series. Maybe you can see it a little bit better if I make it a little bit bigger. So we want to be able to write a power series, to expand it out based on the definition of the summation. And so the summation as n goes from 0 to infinity of c sub n. Well, c sub n, those c's are important. You know what they are. They are from the superposition principle. They're the c sub 1s, the c sub 2s, and so on. Right? You're going to find out that the strength of the solution of a differential equation will be contained within those constants, right? Within those coefficients. There's a summation of c sub n times x minus a to the n. Here, a is said to be the center. If we say that x minus a is equal to 0, then x is equal to a. So on some number line, we have this point A, and then we can examine the neighborhood or the interval about A. So we could talk about the convergence on this particular interval, if that is the question. The geometric series, you recall, is the summation of A times R to the n, where R is a ratio. R is some ratio that's between 0 and 1. So it's a fraction. And so we say that the geometric series is convergent when here R is on this ratio from 0 to 1. Now, it's possible for R to be bigger than that. and for this still to be a geometric series, that's fine. But in terms of the convergence of the geometric series, we want to stipulate that R, the absolute value of R, is contained between 0 and 1. In other words, R must be between -1 and 1. Here, not inclusive of 0. The series is divergent when the absolute value of R is greater than 1. So with this representation, you recall something from Calculus 2, that we're able to write the summation of x to the n as n goes from here 1 to infinity, or particularly from 0 to infinity, to make this geometric series. This is the same thing as 1 over 1 minus x. Do you recall that? The summation of x to the n is equal to 1 over 1 minus x. We use that as the basic function such that we were able to write and other functions utilizing this idea of a power series back in Calculus 2. So in other words, if taking this as the basic model for the summation, so if we had this example, if you had 1 over 1 plus x, using this as our model, this becomes a summation as n goes from 0 to infinity of -x to the n. If 1 over 1 minus x is the summation of x to the n, then 1 over 1 minus a -x is the summation of -x to the n, which anytime a term of variable x is negated, that's how we pick up the alternating series. We factor out a -1 from here. That's -1 raised to the n. This is -1 to the nth power times x to the n. Right. Well, it doesn't matter as long as the function has this form. What if it's 1 over 1 minus x squared? Then the summation has that form still. So this is the summation of x squared to the nth power, or you can write that as a summation of x to the 2n. Right? So we keep this as a basic model. Now, you know that changes when you deal with exponential terms like e to the x or cosine or sine. They have a set summation based, again, on the Maclaurin or the Taylor's expansion. Use the ratio test to find the interval of convergence. Here we've just put in from Calculus 2 the ratio test that here the summation is said to be convergent absolutely if from the limit of the absolute value of the ratio of a sub n plus 1 divided by a to the n is less than 1. If that limit is said to be greater than 1, then we have divergence. And if that limit is equal to 1, then the test is inconclusive. Back in Calculus 2, we said you must apply some other test to determine whether or not it's convergent or divergent. Now, when we do that, we have three possibilities for the convergence. I said that before I ran this recording, but here let's state it. The three possibilities. Let R represent the so-called radius of convergence. That radius could be 0. That radius could be an interval, or could be an actual radius, or that radius could be infinity. So those are the three possibilities here, and I break that down as well. So let R be the radius of convergence, and so here the interval of convergence is from -r to r. Consider a power series, the general nature of it. A is called the center, and so this interval goes from a minus r to a plus r. Here are the three possibilities. That the radius of convergence, it could be 0. If it is 0, then that means that the power series is convergent only at one point, because if the radius is 0, then I'm not moving from A. A is the center. That's where I'm starting. So how far do I deviate from A? Well, if the radius is 0, I'm stuck at A. Right? So if that's be the case, then the power series is only convergent at x equal to A. It's divergent everywhere else. The second possibility is that if the radius of convergence is equal to the infinity, then the entire number line is said to be the convergency for the power series. So the series converges everywhere. There could be a restriction. The power series may be convergent on the interval x minus a less than r. So it's convergent there, then obviously it's divergent elsewhere. Well, where's the elsewhere? Well, the series is divergent if the absolute value of x minus a is greater than r. When finding the interval of convergence, you must check for convergence at the endpoints. Do you remember that from calculus 2? Right. All right, let's see if we can help your memory. Oh, I will help you today. So, well, let's see. Find the interval and radius of convergence for the given power series. I have like 4 or 5 problems here. These 5 problems are identical to the problems in calculus 2. So it's just a review. So what do we do to solve this? You're going to apply, when they ask to find the interval of convergence, apply the ratio test. That's all we have to do. So the ratio test says that the limit as n goes to infinity of the absolute value. Now, since we're taking the absolute value, that -1 to the n, and it'll be -1 to the n plus 1, then downstairs it'll be -1 to the n. Taking the absolute value of that is going to force that guy to be positive. So I'm not going to have to, I don't have to rewrite the -1 to the n or -1 to the n plus 1. Taking the absolute value of that term is still going to be positive. So I'm going to just start with the other terms here. This is x to the n plus 1. This is over n plus 1. That's divided by x to the n all over n. Remember, the ratio test is the limit, it's on the other page, as n goes to infinity of the absolute value of, you take the sequence terms, you look at the n plus 1 term divided by the nth term, right? So we examine here. If this is less than 1, then we have convergence. It converges absolutely, absolute convergence. If it's greater than 1, then we have divergence. So we simplify that. This is the limit as n goes to infinity of the absolute value of x to the n. This is x to the n plus 1. That's the same thing as x to the n times x, right? Now maybe I'll write it like this, and then next time we can just write it. This is over n plus 1, and this is divided by x to the n all over n. So this is the limit as n goes to infinity of the absolute value of x to the n times x all over n plus 1 times n all over x to the n. Hopefully when you apply the ratio test, something cancels out. My wife made a really wonderful dinner yesterday, and I just got to tell you this. She made, those biscuits you get from Red Lobster? She made those. Oh my goodness, man. Oh boy. The food was good, but the biscuits added to it. Oh boy. Okay, I don't know why I'm thinking about that right now. But anyway, we can divide out x to the n, right? So x to the n divided by x to the n goes out. I was in love with my wife all over again, She doesn't even realize that it was just over a biscuit, You give a man a biscuit, he's saved, man. He's happy. Oh boy. So not red. So this is the limit as n goes to infinity of the absolute value of x times n all over n plus 1. Now, so here, this is the limit as n goes to infinity of the absolute value of x. I can break my limit up, if you recall from calculus 1 toward the beginning of calculus 1, that the limit of a product is the same as the product of the limits, right? The limit of the quotient is the same as the quotient of the limits. So if you say the limit of x divided by y, that's the same as the limit of x divided by the limit of y, right? So here I have a product, I have x times something else. So I'm going to take the limit of x, then times the limit of what I have left over here. This is n all over n plus 1. Here, this is also as n goes to infinity. Now, x becomes a constant with respect to the change of n. You see that x becomes a constant with respect to n. N is going to infinity, but at x is staying the same. So the limit of a constant, you recall, is a constant. Now, we don't know the nature of x, so we keep it as the absolute value of x. Here, the limit of, as n goes to infinity, here n is going over positive terms. N divided by n plus 1 is positive, so we can drop the absolute value sign there. I cannot drop the absolute value sign on x because I do not know the nature of x, right? X could be negative or positive, I don't know. But n is traveling from 0 to infinity, so n is positive. And n divided by n plus 1 is still positive, so I can lose the absolute value sign, as we say mathematically, without the loss of generality. Which I just thought that was just a cool phrase, but when I got to graduate school, that was a whole proof in and of itself. You know, does something lose its nature of generality? And you have to actually prove that. And then there's another statement when we say that something is well defined. We say it's well defined. Now that's a proof in and of itself to show that something is actually well defined, which is very cumbersome. But anyway, now what's the limit of n divided by n plus 1? It's 1, right? Do you remember? No. The way you're thinking is something in calculus 2 when we talked about the L'Hopital's rule, that if the numerator is infinity, if the denominator is infinity, then you apply L'Hopital's rule. If you do that, you get the derivative of n is 1. You get the derivative of n plus 1 is 1. 1 divided by 1 is 1. So the limit of n divided by n plus 1 is 1. Right? Yes, sir. But you cannot say that because it's infinity divided by infinity that automatically the limit is equal to 1. Sometimes that's not the case. Right? Well, what happens when you have n divided by n squared minus n, or n divided by n to the third plus 5? The denominator is going to infinity quicker than the numerator, so it's not traveling at the same time, right? So you got to be just very careful, because if it's n plus 1 divided by n to the third plus 5, then that limit is 0, right? Because the denominator is going to infinity quicker, right? And so the numerator, its rate is slower than your denominator. So you get close to 0 quicker than you would anything else. Yeah, the powers are important. You remember the limit is the same thing as looking for the horizontal isotope. Do you remember that? The horizontal isotope. The horizontal isotope had 3 possibilities. You look at the power of the numerator divided by the power of your denominator. If the powers are the same, then you divide by the leading coefficient. N divided by n, you get 1. Here, This is n to the first power for the numerator. Downstairs is n to the first power. You have the same exponent, so you divide just the ratios, the leading coefficients. Here, um, what is the coefficient for n up top is 1. The coefficient for n plus 1 downstairs, that's 1. So 1 divided by 1 is 1. The horizontal isotope also said that um, if the degree of the numerator is less than your degree of your denominator, then the horizontal isotope is equal to 0. Same thing as the limit. Right? So in algebra, we talked about the horizontal isotope. In calculus, we said that's the same thing as the limit. So you were talking about the limit back in algebra, just didn't know it. Just a different name. Um, in the Old Testament, when the Bible said that God had grace with Noah, see, we didn't know that grace that God was talking about was the sacrificial blood of Christ. Right? The New Testament, he says it, what it really is. In the Old Testament, he just said it was grace. It's the same thing. Wow. Okay, don't get too excited. Might get happy. Amen, amen. And look, was that week before last, Micah, when I came to? Was it last week? Time is so scary. And Michael was in a revival down in Moulton and went out. Was it Monday night? Went down there to hear him preach. Great preacher. I got a steak. Because when I got there, we went to that restaurant in Moulton. What is that, Western Sirloin? Went there, and they only had catfish, and I don't eat catfish. And so I just got I think a ribeye or something like that. I'm trying to watch my red meat intake. But anyway, let's get back to this, right? Okay, so the third possibility for the horizontal isotope, I'm sorry, is that if the degree of the numerator is greater than the degree of your denominator, then there is no horizontal isotope, or that the limit is equal to infinity. Right? So here, the limit of n divided by n plus 1 is 1. So I have the absolute value of x times 1. Now how do we get absolute convergence from the ratio test? This limit has to be what? Less than 1. Right? Now I can restrict that because here the n's went out. Right? It was n divided by n plus 1, but the limit of that is equal to 1. So the only thing that I'm containing here is a containment for that x. Right? So what that implies is that the absolute value of x is less than 1. Now by definition, this is the same thing as negative 1 is less than x is less than 1. Right? So this is the so-called interval, but I need to check the endpoints to see if it's going to be negative 1 less than or equal to x, or x less than or equal to 1. So check. The endpoints. So we check here first at x equal to negative 1. So I go back to the original power series and I plug in x equal to negative 1. So this is the summation as n goes from 1 to infinity. It has a negative 1 to the end there. This is divided by n, and this is times x, which now is set to be negative 1, and that's x raised to the n. This is the summation. What's negative 1 to the n times negative 1 to the n? Huh? Oh, yes. 1 to the n, which is just 1, right? Right, negative 1 times negative 1 is going to be positive, right? So this is n goes from 1 to infinity of 1 all over n. This is convergent or divergent, and what's your reason? This series, it converges or diverges? Huh? Now, I don't know what it converges to. Don't get the series and the sequence mixed up. The sequence is 1 over n, but the series is the summation of 1 over n, which that starts from 1 plus a half plus a third plus a fourth plus a fifth plus a sixth plus a seventh all the way to, right? So does that sum up to equal 0? No. Right? So don't get confused. Remember that back in calculus 2. Don't get confused with a sequence versus a series, right? A series just adds up all the sequence values. Yes, sir. So this is convergent or divergent? That's my question. And why? I don't want to hear anything else. As a moment, I don't want to hear anything else. I just want to know if it's convergent or divergent and why. Yes, sir. It's divergent using the P-series test. Yes. You have P equal to 1, right? N to the first power. It's divergent. Very good. P-series divergent. Do you know that when you take a string and you thump it, it has a vibration, right? And you want to calculate, the measurement of that. That's a harmonic series. That's what that is, right? Yeah. Even the drum and the vibration, right? That goes back to Hooke's law and really back to chapter 5, section 1 as well. It's the same thing. So when P is equal to 1, you get the harmonic series. I mean, it's divergent in nature, but it's important to when you examine the measurement of the string instruments. Very good. So that happens there. Now, what about at x equal to 1? We have the summation as n goes from 1 to infinity. That negative 1 to the n is in the problem. This is times 1 to the n all over n. Let's simplify that. This is the summation as n goes from 1 to infinity of negative 1 to the n all over n. This is divergent or convergent, and why? I even have a better question. Does it converge absolutely, or does it converge conditionally? And why? Okay, maybe it's not a better question. You ain't saying anything. It converges. Okay, you're saying it like maybe. Oh, I'm sorry. No, I need a theory. Is that alternating series? Right? Remember the alternating series test? Yep. It says that one, if it's monotonic, that is, if it's steadily increasing or if it's steadily decreasing, right? When we look at the sequence values, 1 over n is steadily decreasing, right? It goes from 1, 1 half, 1/3, 1/4. It's getting smaller and smaller. That was one test. That's one part of the test. There's two parts to that alternating series test. One, is it monotonic? That is it going to be decreasing always? Is it increasing always? And then secondly, what's the limit of the sequence? If the limit is equal to 0, then it's by the alternating series test, it's convergent. What's the limit of 1 over n? That's 0, right? Because it's a sequence, right? You don't get confused again with the series. The sum of the series is said to be its limit. And you got various tests to try to find, the so-called summation for a series that we talked about in calculus 2. But here, this is an alternating series, and it's convergent. So this converges by the alternating series test. I'm going to move on because I want to. So watch this. So here we say that the interval convergence is it it was divergent at -1, so it's parentheses at -1, comma. But at 1, it was convergent. So it's 1, and then we put the bracket there, right? That means that it also contains 1. All right? Is that okay? Okay, good. Let's look at this one. Apply the ratio test. This is the limit as n goes to infinity of the absolute value of x to the n plus 1 over n plus 1 to be squared divided by x to the n all over n squared. This is the limit as x goes to infinity of the absolute value of x to the n times x. X to the n plus 1 is x to the n times x. And then this n squared goes upstairs. That's divided by that x to the n times n plus 1 all to be squared. Now the x to the n's cancel out. So this is the limit as n goes to infinity of the absolute value of x times n squared over n plus 1 to be squared. Again, I do not know the nature of x. It could be negative or positive, so we leave that in absolute value sign. But here the n values are traveling over positive numbers. N goes from 1 to infinity, or 0 to infinity. Well, here it's going from 1 to infinity. And then n squared is positive. N plus 1 is to be squared is positive as well. What is the limit of n squared divided by n plus 1 squared? 1. This limit here, it goes to 1, right? The ratio test to have absolute convergence, we say that this limit here must be less than 1. So what this implies is the absolute value of x times 1 is less than 1. So here this gives us -1 less than x less than 1. Again, we check the endpoints. Now the next problem, we won't get the absolute value of x less than 1, so I don't want you to think that all the values are supposed to come out to be 1 in some type of way. That's not the case. Just these two lame problems right here. Okay, so here we check at x equal to 1, -1, excuse me. So wherever I have x, I'm going to put -1. So this is the summation as n goes from 1 to infinity of 1 over n squared times -1 to the n. This is the summation as n goes from 1 to infinity of -1 to the n all over n squared. Divergent or convergent, and why? This converges by 2 tests. It's a p-series convergent, right? Because p is equal to 2. Remember, it also by the alternating series test is convergent, right? So if that be the case, this has even a stronger claim that it converges absolutely. But here the simple statement is that it does converge. Converges absolutely means what? That if I take the series and if it converges as it is, and then if I take the absolute value of the sequence values, and if they're convergent, then we say that the series converges absolutely. Take the absolute value of the sequence values here, that is, see we have -1 to the n, take the absolute value of that, it gives you 1. So what's the summation of 1 over n squared? Is that convergent or divergent? It's convergent too by the p-series. So it converges in both cases, so we say that sense in calculus 2 is that it converges absolutely. It converges all by itself. Take the absolute value of those values, it converges there. That's a stronger case if it converges absolutely. I mean, not only you clean, what they're saying is you're really clean. You know, because sometimes a person can be clean, like the clothes are nice, the hair is fixed, whatever, that kind of thing. But man, their toes could be just cruddy, but you don't know that. You know, they probably didn't wash up under their arms, but you don't know that unless you get up close. You may say you can go to the store and get new clothes and put new clothes on. You can still be dirty. And we got to be very careful because a lot of people are trying to put on nice things and then they're trying to say that they're in some kind of way sanctified. No, sanctification, this cleanliness is in the heart. Right? You can talk like you're a religious person. Right? You can even do some good things. You can still go to hell. Yeah. I don't mean to preach to you, but let's go back and look at this right. Boy, this is good stuff. It's good stuff. Yeah. People ask the question, oh, why do you teach the mathematics? And when I teach it, all I see is God. Because when you talk about convergency and traveling to infinity, I'm trying to get close to God. That's what the limit is trying to do. Yeah, that's what the numbers are trying to do. The heavens declare the glory of God, and the firmament showeth forth His handiwork. That's what David had in mind. That's what Isaac Newton had in mind because he loved the Lord. And he was examining God's handiwork. That's what you do as an engineer. You're examining God's handiwork. That's all we do. Okay, anyway. This we said here, getting back to this, I'm getting carried away. Check at x equals to -1. This guy converges about the P-series test. Okay, so now we check at x equal to 1. This is a summation as n goes from 1 to infinity. The problem there was just 1 over n squared times 1 to the n. This is a summation as n goes from 1 to infinity of 1 over n squared. P-series convergent. Right. So this first one, it converges by the P-series test in the alternating series test. So here we get convergence on both sides. So here this interval convergence is from -1 to 1. We put brackets on both sides, right? Let me do one more here. I hope this is the one. And then after that, we want to look at how to actually solve. Well, I guess I got to do 2 more here. So let's do this one. This is the limit as n goes to infinity of the absolute value of 2n plus 1 times x to the n plus 1 over n plus 1. So these are the terms for a sub n plus 1. Then that's divided by the a sub n terms. So it's divided by 2n times x to the n all over n. Now we can simplify that. This is the limit as n goes to infinity of the absolute value of 2n times 2 times x to the n times x. Now that n downstairs, he jumps up in that division process. This is divided by n plus 1 2n times x to the n. Now let's see. 2 to the n cancels out, x to the n cancel out. I think that's everything that cancels out. So we have here left the limit as n goes to infinity of the absolute value of 2 times x times n all over n plus 1. Now notice here that this 2 times x, I could bring that out from the limit because it's not in the process. It's not in the limitation process. Here the 2 is fixed, x is fixed, but the n's are changing. So we can write this as the limit as n goes to infinity of, I need to take that out, the absolute value. I'm sorry, that's 2 times x here times n over n plus 1. The limit of n divided by n plus 1 is 1. The ratio test says that we have convergence if this limit is less than 1. So this is the absolute value of 2x is less than 1. So this implies that the absolute value of 2x is less than 1. That is negative 1 less than 2x less than 1. Now you divide by 2, so we get negative 1/2 less than x less than positive 1/2. The only thing that we've done to this problem is just to apply the ratio test. That's all we've done. So now we check the endpoints. Check at x equal to negative 1/2. So we go to the problem. So we have here the summation as n goes from 1 to infinity. This is 2n divided by n, and then it's x to the n, where x is negative 1/2 to the n. To simplify that, this is the summation as n goes from 1 to infinity. This is 2 over n, 2 to the n divided by n, excuse me. And this is times, I'm going to break this negative 1 over 2 to the n down. This is negative 1 to the n. Let's break that as negative 1, take that out. And then I have this 1/2 to the n. This guy becomes an alternating series because of the nature of the negative. So this is the summation as n goes from 1 to infinity of negative 1 to the n. You see the 2 to the n's cancel out? This is 2 to the n, and over here this is 2 to the n downstairs, right? See, they cancel out. This is what 1 to the n, which is just 1 divided by 2 to the n. So what I have left then is that negative 1 to the n times 1 over n. Is that convergent or divergent? It's convergent. Why is it convergent? By alternating series, right? It diverges by the p series, right? So that's why we call that conditionally convergent. It converges in one test, it diverges in another test. But for us, I mean, conditional is still okay. It does converge. And I'll show you in the next step the reason why it's said to be conditionally convergent. Here, this converges by the alternating series test. Now we check at x equal to 1/2. So this is the summation as n goes from 1 to infinity. We have that 2 to the n over n. Here this is times 1/2 to the n. You see where I break it down for you. This is a summation as n goes from 1 to infinity. This is 2 to the n over n times 1 over 2 to the n. The 2 to the n's cancel out just like before. What I have left is the summation as n goes from 1 to infinity of 1 over n. Is this convergent or divergent? It diverges, right? About the P series. See how, in one sense, with that negative 1 to the n, it converges. You get rid of that negative 1 to the n, it diverges. So that's why we say conclusively that it converges conditionally. But here, this diverges by the P series test. So we were good at negative 1/2, but we're not so good at x equal to 1/2. So here we have closed bracket at negative 1/2, comma, and then we have the positive 1/2 is open there. Do one more here, and then I'll work a problem. Sorry. Do one more of these. I want to do one where it either has the radius of, see, our radius of convergence here that you've seen. Like if it's from negative 1/2 to 1/2, capital R is equal to 1/2. That's the radius, right? The radius is just half of the interval, the half of the distance of the interval. Uh, if you go from negative 1 to 1, then the radius is said to equal to 1. But what if the case that you have the radius of convergence is 0 or the radius of convergence is infinity? Let's work one now where the radius of convergence would be infinity. So we apply the ratio test. The limit as n goes to infinity of the absolute value of 5n plus 1 times x to the n plus 1 all over n plus 1 factorial, and this I just say it's divided by 5n times x to the n all over n factorial. So this is, yes, the limit as n goes to infinity of the absolute value of 5n times 5 times x to the n times x. Now when I do the division, this becomes the n factorial. It goes upstairs. That's divided by n plus 1 factorial. And then what comes downstairs would be that 5n and then x to the n. 5 to the n and then x to the n, excuse me. Now the 5 n's cancel. Not as good as 5 a's. That's a Greek restaurant over by my house in Harvest. I had the tilapia fish dinner on Saturday. It was really good. Anyway. My wife doesn't like that place. I don't know why. I think the only one in my family that likes it besides me is my oldest son, EJ. And he gets the gyro sandwich and I always get the grilled fish sandwich. My wife, she's very high class. So, you know. I should have told her, 5A's, their score was 100. Cause she gets them maybe because she thinks that I look for places that has a score less than 86. You know, she's like, you like those places? I said, yeah, I know, it's kind of good. You know, you gotta see some grease stains somewhere. You know, a couple of flies, it's okay. You know, I mean, the flies gotta eat. I tell you what, I went to McDonald's and it was years ago when Johnny, my middle son, was like a little kid, and he always just loved chicken nuggets. I don't know, kids with autism, I don't know, chicken nuggets and french fries must be like, you know, they're born with that predisposition. They got to have french fries and chicken nuggets. Anyway, man, one of his chicken nuggets fell in between the seat, like his little car seat, whatever. And I didn't know. That thing stayed down there, man, for months. Let me tell you, the maggots wouldn't even eat it. The flies wouldn't even fly. I mean, it just stayed there. I'm like, this is not even food, guys. You know, we're eating plastic, man. You know, food. If it's food, it's supposed to decompose. That's how God made it, right? I mean, even the insects wouldn't even touch it. So that's why I go to restaurants with the score less than 87 because they got flies around it because it's real food. Anyway, I'm just tripping. You got a restaurant flies don't hang around in mayonnaise, you know. But anyway, my wife gets on me about that. But let's move on. So the 5 to the ends, not 5a's, but 5 to the ends cancel, x to the end cancels. We have left the limit as n goes to infinity. This is a 5 there, and x, so it's the absolute value. 5 times x times n factorial all over. Now you can write this n plus 1 factorial, remember, as n plus 1 times n factorial. Right? So this is n plus 1 times n factorial. In other words, if you got 4 factorial, you can write that as 4, remember, times 3 times 2 times 1. Or you can write 4 factorial as 4 times 3 factorial. Right? Means the same thing. So here, we do that to show the relationship with the numerator and our denominator, so the n factorials cancel out. So I have left here the limit as n goes to infinity of the absolute value of 5x times 1 over n plus 1. This is the absolute value of 5x time, because the limit of this constant is a constant, times the limit as n goes to infinity of 1 over n plus 1. What's the limit of 1 over n plus 1 as n goes to infinity? 0, right? That's 0. Now what this means is that, because we're looking for the choices of x by which this power series is convergent. But every time you take any choice of x and you plug that into that limit, you're going to get, like, if, say, for example, if x is 1,000, I have the 5,000 times the limit of 1 over n plus 1, I'm going to get 0. Doesn't matter. For any choice of x you get, the limit is going to always equal to 0. Which means that for any choice of x, the limit is 0. That means that my radius of convergence is infinity. The radius is based on the choice of x, not n. Right? X can be anything here, and I'm going to still get that choice of x right here times the limit of 1 over n plus 1. I always get 0. Doesn't matter. Yes, sir. Just in layman's terms. Exactly. So here, since for any choice of x, this limit is always 0. This implies that the radius of convergence R is equal to infinity. With the interval of convergence, because that's too long of a sentence. The interval of convergence is from negative infinity to positive infinity. Okay. Okay. Good. Oh, boy. Huh? Mercy. Yeah, I think I bent this thing. Hopefully the sound is still working. I forgot about, got the headphones on. Can you give everybody one of those? So the next phase that we look at is how to solve a differential equation using power series. What I'm passing out is what I have here, but I want you to see it as we work the problem. as well. So there are 7 steps to solving a differential equation using the power series. So as we work the problem, I refer to these steps. So you want to get a common index, and I'll show you what that is. Replace n with some k factor. That k term would be the index. Factor out x to the k in some way. Write all the summations as one common summation. Step 4, get a formula for c sub k. Thank you. Solve for the coefficients c sub k. Get a pattern for c sub k. Step 6, and then 7, write the solution. So here, let's take this problem, number 35. It says solve the differential equation in the manner of the previous chapters, and then compare the result with the solutions obtained by assuming a power series solution. Here, the way the power series is written in its actual form is the summation as n goes from 0 to infinity of c sub n times x minus a to the n. But for these problems, a is equal to 0. So since a is equal to 0, then we just have the summation of c sub n times x to the n. You see that? Right. You don't see it because a is equal to 0. Right. Okay. You see what I'm saying, Christian? Okay. So, why is this important? It's important. What question am I raising? Why is it important to solve a differential equation by power series? Here's why it's important. If you cannot solve it by any known method, then you can always use the power series solution. Right? Up until now, we've dealt with known methods of solution: variation of parameters, Cauchy-Euler, the linear Bernoulli, substitution, homogeneous. We have known forms of solving. But what if you run into a problem, and you will run into problems in life where you have no idea of how to solve that? But there is another possibility. You could use power series. This process takes a little bit longer. A lot of your computer programs like Maple and MATLAB and Mathematica, they have these code sequences built in them. A lot of times you type in a problem and it'll solve it on the computer, and it'll give you the solution in power series. Then you have to go in and tell the program to give you the solution, in an exact form, because the computer itself is always reading, to be honest with you, all of the solutions that it's programmed to give it to you in the power series format. So you can tell the program to convert that to just a solution that you've kind of seen before. In this section, we do a couple of things. We say solve the problem by a previous method, and then solve it by the power series. Your answer should be the same thing. Then later on, like in sections 6.2 and 6.3, we won't have a previous method to solve it. And so you won't be able to rely on, okay, let me work this a different way and see if I get the same answer. Because there are problems out there where there is no other form to solve except for power series. One of the second or third tiers, I would say the second or third tier from this would be solving a differential equation by Fourier analysis. And if you ever heard of that phrase before, this is the foundation for it. The second tier is solving using Basel's equation, and that's, I think, in like section 6.4. We don't have time to even cover that, but you get into more specific types of differential equations and how to solve their type. So here we look at the first way is to, I should say A, solve by a previous method. Well, this is a differential equation with constant coefficients. So my auxiliary equation here would be m minus 5 is equal to 0. That implies that m is equal to 5. So here, y sub c, my complementary solution, would be c sub 1 times e to the 5x. Right? Does that sound familiar? Now, I want you to recall that e to the x, this is from calculus 2, is equal to the summation as n goes from 0 to infinity of x to the n divided by n factorial. Do you remember that? Okay. But this problem is e to the 5x. So e to the 5x is equal to the summation as n goes from 0 to infinity of here, wherever I have x, I'm going to write 5x. So this is 5x to the nth power all over n factorial. Or, simplify that, e to the 5x is equal to the summation as n goes from 0 to infinity of 5 to the n times x to the n all over n factorial. So my answer when I work part B, that is solving by the power series solution, my final answer here should look like the summation of 5 to the n times x to the n divided by n factorial. So here I'm going to go through these steps. So here we have the problem, y prime minus 5y is equal to 0. So here they tell us that assume that y is of the form, the summation as n goes from 0 to infinity of c sub n times x to the n. Right? That's what's here assumed in the beginning. So if this is the case, if I take the derivative of y prime, this is the summation as n goes from 0 to infinity of c sub n. Here the derivative is applied to x, right? So this is n times x to the n minus 1. So I take the problem, and the problem is y prime minus 5y. That's equal to, well, y prime is the summation as n goes from 0 to infinity of c sub n times x to the n minus 1. Then it's minus 5 times y, but y is the summation as n goes from 0 to infinity of c sub n times x to the n. All right, so now look at my steps. First step is get a common index. The index here is going to be this k factor. What does that mean? Here, the index now is n. N is going from 0 to infinity. Right? The goal is to be able to write this summation, these two summations as one summation. But I can't do that because I have here x to the n minus 1, or here I have x to the n. Those exponents are different. You need to be able to get the same term in some kind of way. Well, notice here that for this first summation, doesn't happen for the second one, but for this first one, if I evaluate the summation at n equal to 0, I get c sub 0, which is some constant that I don't know, times 0 times x to the 0 minus 1. Which basically that 0 there, when n is equal to 0, that first term is going to be 0. So it's safe to say, without loss of generality, that if I can start the count here at from n goes to 1 to infinity. Because that 0, that first term was 0. Right? You plug in n equals 0, I'm going to get here c sub 0 times 0. 0 times anything is 0. Then it's going to be plus, that the summation evaluated at n equal to 1, plus the summation evaluated at n equal to 2, plus and so on to infinity. So here, you can write this as the summation as n goes from 1 to infinity of c sub n times x to the n minus 1. That's the only thing that I did the change on. Then minus 5 times the summation as n goes from 0 to infinity of c sub n times x to the n. So now I'm working on getting a common factor, a k factor. So what I'm going to do here is I'm going to always look at my exponents. I'm going to say let k equal to n minus 1. Let k equal to n minus 1. Over here, the second summation, let k equal to n. So if that's the case, then I'm just going to solve for n just from this let statement. So I get k plus 1 is equal to n. There's nothing to do over there. So I'm going to replace all of my n's with the k's. So this is the summation. Here, this is k now. Right? Well, if n is 1, 1 minus 1, k starts at 0 to infinity. Right? And it looks like, it ought to be like infinity plus 1 or infinity minus 1. That's still infinity. Right? So we make the adjustment at the initial start, and we let infinity do its job at the end. Because infinity plus 1 is still infinity. Boy, I tell you. Okay. Gotta stay focused. C sub n, but n is now k plus 1. Times n, times, parentheses, k plus 1. Times x to the n minus 1, but n minus 1 is k. And this is minus 5 times the summation here. K is equal to n, so this is k goes from 0 to infinity of c sub k times x to the k. That's all equal to 0. Now look at my step there. Now I can factor out x to the k because they both have an x to the k in them. See that? It's a common factor. So this is step 1. Step 2, you can write this as the summation as k goes from 0 to infinity. I'm going to factor out that's x to the k times brackets c sub k plus 1 times k plus 1. Moving over. Now, how can I factor out and write this as one summation? 2 reasons. X to the k is common, right? And then they're also starting at the same pivot position. They're both starting, k goes from 0 to infinity. If they start off at different locations, then I can't combine the summations. But if they start off at the same thing and they have a common factor, I can factor that common term and just write all of these summations as one summation. So here, this was this c sub k plus 1 times k plus 1. I factored out that x to the k. This is minus 5 times c sub k. Close that up. That's equal to 0. So this was step 3. Let me pinpoint this. And then step 4, I wrote all this as one summation, so I did those 2 steps the same. This is a 0. Steps 2 and 3, excuse me. Good. All right, now, is the summation of something set to equal to 0, that x to the k is the same term. You remember how when we were doing the to find the interval of convergence, you have like that absolute value of x, and then it's times the limit or something like that. This is the same x, by the way. It's the same x value. Here, the x value is what I'm determining in terms of whether or not it's going to be convergent or not. So this summation to equal to 0, the emphasis is not on x. The emphasis here, what makes the summation 0, would be these terms here. Why is that? The, the solution is on the interval from 0 to positive infinity. That means that here x cannot equal to 0. But something has to be 0 to make the summation equal to 0. So it has to be the terms here. So step number 4, we're going to get a formula for C sub k. So that is step number 4. I write C sub k plus 1 times k plus 1 minus 5 times C sub k is equal to 0. Solve for C sub k plus 1. I know my time is up, but this is type of problem that you get in the middle of it, you really just got to finish it, because if not, come back later, you'll just be completely lost. So solve for C sub k plus 1. I'm going to add 5 C sub k on both sides. So I have C sub k plus 1 times k plus 1 is equal to 5 times C sub k. Divide both sides by this k plus 1. So I have C sub k plus 1 is equal to 5 times C sub k all over k plus 1. That's step number 4, where it says get a formula for C sub k. This is my formula. Now the next thing that we have to do is to determine these coefficients. Well, here's how we do it. We take this formula, and then I just start counting from k goes from 0 up until, maybe k goes to 4 or k equal to 5 to get a pattern. Here when I'm trying to build a pattern for C sub k. So here, let's take k to equal to 0. So I get, just look at the formula. That's all I'm going by now. So here I get C sub 1 is equal to 5 times C sub 0 all over 1. Let k equal to 1. I get C sub 2 is equal to 5 times C sub 1 all over 2. Let k equal to 2. I get C sub 3 is equal to 5 times C sub 2 all over 3. K equal to 3. We get C sub 4 is equal to 5 times C sub 3 all over 4. And I reckon that's enough to build the pattern. Let's see. Now this is just 5 times C naught. We simplify. This is C sub 1, but C sub 1 is 5 times C naught. So this is 5 times 5 times C naught all over 2. This is 5 to the second times C naught over 2. What about this one? This is 5 divided by 3 times C sub 2, but C sub 2 is this. So this is 5 times 5 to the second times C naught all over 3 times 2. Now look at the pattern so far. This is 5 to the third times C naught all over 3 factorial. Right? 3 times 2 is 6. It's the same thing as 3 factorial. Same thing here. Look at this. This is 5 squared times C naught all over 2 factorial. Let's do one more so you can see it. This is 5 over 4 times C sub 3, but that's the C sub 3 up above. This is 5 to the third times C naught all over 3 factorial. Well, 4 times 3 factorial is 4 factorial. So this is 5 to the 4th power times C naught all over 4 factorial. So this is step number 6. We have a pattern for this C sub k. So So here, solve the coefficients for c sub k. That's step 5. Right. Step 5. And then you get the pattern. Let's see. Oh, spaces run out. Let's see. Add a page. So y is said to be the summation as n goes from 0 to infinity of c sub n times x to the n. Now, just write that out. Count when n is 0, so this is c0 times x to the 0. So this plus c sub 1 times x, right, when n is equal to 1, plus when n is equal to 2, c sub 2 times x squared, plus when n is equal to 3, c sub 3 times x to the third, plus, and so on. Now, for the problem, I get y is equal to, I get the c sub naught plus c sub 1. Go back. C sub 1 is 5 times c naught. So I'm going to replace that over there. So c sub 1 is 5 times c naught times x plus that next term, c sub 2 is 5 squared times c naught divided by 2 factorial. We see the pattern really, right? 5 to the third times c naught divided by 3 factorial. So we see that pattern. So we're going to replace all the c's with what they are based on that c naught. So this is 5 squared times c naught times x squared all over 2 factorials. Put one more here, plus 5 to the third times c naught times x to the third all over 3 factorial, plus, and so on, plus here's the pattern. This looks like 5 to the n times c naught times x to the n all over n factorial. This is the n there. All right. That's the pattern. That's step 6. A little bit of shorthand. So this is step 6. So now, here's the solution. Y is equal to, why don't you just factor out c naught from all of them? This is c naught times parentheses 1 plus 5x plus 5 squared times x squared over 2 factorial plus, I think we get it. Oh, this is not finished. This is plus and so on, right? Sorry about that. Plus and so on, plus 5 to the n times x to the n all over n factorial, plus and so on. Keeps on traveling. So I can write this now as a summation. Y is equal to c naught times the summation as n goes from 0 to infinity. That's the pattern. 5 to the n times x to the n all over n factorial. Watch this. This is the same thing as c naught times the summation as n goes from 0 to infinity of 5x to the nth power all over n factorial. Go back and look at part A, but isn't that the same thing? We called it C1, but it doesn't matter. This is the same thing as c naught times e to the 5x. Go back up above. See that when we first started that, part A, see that? E to the 5x, just based on the Taylor's expansion, is the summation of 5x to the n divided by n factorial. Well, you've just deduced that based on the power series solution, and you came up with that the old-fashioned way. Thank you. Do the homework there for this section, and don't forget, if you haven't taken your test, it's waiting on you over there in the testing center. Have a good day.